Okay, hello, good afternoon. Okay, so this talk is just more related to the application side. Okay? Just to put the things in context, okay, this is the whole Admire framework that we are introducing, discussing today. And these talks will focus on the application side. That is this red box on the right. So the idea is to answer the question, if I have an application that could be interested to run this framework, just to see how it can be integrated and how we can use the new capabilities that we are developing in this project, for instance, malleability or monitoring part or integration with the intelligent control. Okay, so the talk will have two parts. I will give the first one that is more related, more theoretical one, how from the programming point of view, how the application is integrated with the different Admire calls. And my colleague Javier will do a practical demo of real applications running on a real cloud. Okay. Just before starting the credits, this work was mostly developed by my colleagues Javi, Alberto Cascajo, that I think that is connected online, and also Clement, that is around here. So just for beginning, just a brief summary of the things that we have done. Just before the project, we had a runtime that provides malleability to MPI applications. The runtime is Flex MPI. So in the scope of this project, we have extended Flex MPI to Fortran applications. So now we are able just to integrate both applications in C and Fortran languages. This was a quite intense development in our group. The second thing is that we also extended Flex MPI to provide new capabilities developed in the Admire project. So now there are new functionalities. Some of them will be introduced by me later, okay? Especially the connections with the intelligent controller. Another interesting thing is that we have developed a library called libICC. Okay, so this library, if we look at the figure, this library permits the connection of the applications with the intelligent controller. Note that the connections are bidirectional, okay? Because the applications are able to receive commands from the intelligent controller, for instance, expanding or reducing the number of processes, but also they are able to send informations and user hints to the intelligent controller. For instance, it's necessary, we are entering in a malleable region, or the application has certain characteristics that fits very well, for instance, with the I/O or the compute phases. So this is another part, and the connections are not only with the intelligent controller but also with the SLAM. Okay, because the big problem that we found was just not the application malleability, but the resource allocation, how we are able to increase or decrease the number of compute nodes, and use this feature just with the applications in order just to, for instance, populate new nodes that have been allocated by the SLAM. So finally, Javi was working on that, and he found a nice solution that permits to do that. And I think that he will introduce this solution in his talk later. Another contribution that we have done is that what is mentioned here, new span shrink operations. So before that, all the process creation and destruction was done in MPI, using MPI functionalities. And one of the things that we realized in this project is that some applications include checkpointing routines, and in this case, it is much more efficient doing these operations leveraging the checkpointing. Okay, so we created what we call start-stop operations that are able to create and destroy processes relying on checkpointing. This is interesting, for instance, for NEC 5000 application. And in this case, using the same interface as Flex MPI. So what we have is a common interface. We are able to apply malleability using different strategies according to the application capabilities. Okay? So it's another interesting feature. And finally, we have tested our framework with different applications. Some of them, they are part of the use cases of my project. For instance, Compass Plus and NEC 5000, numerical kernels, and other applications like Epigraph that are also integrated with Flex MPI and libICC. Okay. So in my talk, I'm going to focus more in the programmability part of the integration. So this is the outline of this section of the talk. So let's start with the use case. Okay. So what we choose is just a iterative kernel. We can see here. So in the top part of the kernel, there is an initialization section. Okay, we see empty lines because maybe there is extra user code there. Okay, so we have an initialization that are, you can see the MPI init routine, typically from MPI applications. Maybe you can get the number of ranks or the rank assigned to each process. And then we represent inside a loop, a while loop, the iterative section. So there is where the numerical code is placed. And for instance, there is an MPI communication routine as a reduction, as an example. So it's a very, very simple, let's say, a template of an iterative kernel. And what I want to show you today in this talk is how we can extend this kernel and implement it in Admire framework. So the figure on the right will include the new code with new lines, new functionalities that needs to be included for having both malleability and integration with the intelligent controller. So the final code is on the right. It's a bit more complex than the original one, but I will explain it little by little. So let's go over the different functionalities that we have developed, and I will use this example as a use case, okay, for describing each one of them. So first one is the header. Okay, we have what we show in the figures is just the interface that we have developed both for C and Fortran programming languages. So we have an eMPI header with all the internal variables that are user transparent, and also all the initialization and termination of Flex MPI and libICC are included by means of wrapping the MPI init and finalize function. What I'm saying is that it's user transparent again, okay? So if we look at the code, we have an extra header. We can see the rect boxes on the top, an extra header, and MPI and finalize sections are exactly the same as the ones before, but by means of the wrapping, they include the Flex MPI functionalities inside for just starting the environment, the runtime. So this is the first thing. Second thing is the communicators. So in the standard MPI program, we have the word MPI word communicator. In this case, we have developed a specific Admire communicator that is called ADM. Okay, it fits very well with the project, we think. And the idea is that it's a malleable communicator, which means that if new processes are created or destroyed, the communicator contains the information of them. Okay. In case of C, all the transformations of the communicator are transparent. We don't need to introduce extra code. But for Fortran, we need to introduce a function just for updating it. Here we can see the example. And we see that the only things that we need to do is just change the communicator name. No more than that. No updates, nor anything. Both, for instance, at the beginning in the initialization part and at the end in the MPI reduce operation. Okay. So far we have the starting of the framework. And now we'll focus on the iterative part, okay? So this iterative part is subjected to malleability, is the one that according to the intelligent controller, we can increase or reduce the number of processes. For doing that, we define control points. Control points is basically the code section that is subjected to malleability, okay? For defining these control points, we define malleable regions that are basically two MPI, flex MPI, sorry, function calls, okay? One for entering in the malleable region, and the second one for exiting in the malleable region is this one, okay? So you can see here better, maybe in the code, okay? So in the iterative part is delimited by both these regions. And there is another thing, is that if, for instance, one process is removed from the execution because the application execution is shrink, then we need to detect what is, which one of the process is. And for doing that, we use the status variable that is captured at the end of the malleable region, okay? So getting this value, there are two different possible values. And if it is removed, we can see in the box, then this means that the process is no longer involved in the execution and exits the malleable part and then executes the finalized. So the process that is removed is finally destroyed and all the resources are freed, okay? In parallel with this, of course, after destroying the processes, if it is running in an exclusive node, then the node is unallocated, okay? Deallocated, sorry. It's deallocated, so both the computational and physical resources are deallocated, are freed, and we can just have more space in the system for other applications, okay? So this is how we detect that. And then an interesting characteristic of Flex MPI, this framework, if I'm going back to the beginning, we see that there is an arrow that goes down, okay? These arrows represent the monitoring metrics that are captured by the Flex MPI. So we use a PAPI, monitoring library, in order to capture not only execution times, but also different kinds of events that can be configured by the user, for instance, flops, cache misses, memory accesses, etc. So the user can capture different metrics that are sent to the monitoring management that is related to work package 5. And we think that is interesting because, of course, Admire includes different components that collect monitoring components, but most of them are oriented to a compute node level. So with this approach, we are also able to capture information at application level, okay? And we have, for instance, done work related to, for instance, scheduling of malleable applications that combine all the monitoring metrics, okay, in order to develop more precise application performance model, just to support the malleability scheduling, okay? How these metrics are introduced is basically by means of two function calls in the same, following the same philosophy as with defining the malleable section. We define a monitoring section, okay, by means of monitoring service and start and stop by means of two flags, okay? You can see the flags here in the code. This should be inside the malleable section, and that permits to capture the metrics just in a specific code section. With a thing that is interesting, just the kernel in this case, no? The one that is executed and the one that we want to optimize. So the last thing is how to keep and propagate the system state when the malleability is applied. I remember at the beginning of the project, we have interesting discussions with, I think that was Maximo, that we discussed about the system state, that you have previous experience with that. So that could be a challenging thing just to keep the system state when, for instance, application is expanded, so more resources are used. Okay, so the final approach that we are following is to use function calls that permits to store information in Flex MPI and then recover the information when new processes have been created. One example is in here, for instance, that is the iteration number. So we have a kernel that executes in the while loop different iterations. Originally, we assume that it is starting 0, but for instance, if iteration 1000, the number of processes is increased, then the new processes have to know what was the iteration value at the point of the expansion. Okay, so this is done by this function that is able just to register and then send to the new processes, in this case, the global iteration value, the variable that is kept. Okay, so what we have done is that we have extended this idea to multiple data types. Okay, so one example is register simple data that are integers and double values, so we can register the information and later recover it. And the second thing is that we have the same for arrays. Okay, not only single data types, but also arrays. Here's interesting because arrays can be replicated across the processes or distributed. Okay, and this is a work in progress, but the idea is just to incorporate automatic data redistribution when a malleable operation is carried out. Okay. So we have arrays and also we have strings. Okay, so with this and some little user intervention, we will be able to just keep and propagate the system state during the application execution when we have malleability, of course. Okay. And so this is the interface. The previous ones were for storing the system state and have another interface just for getting the values. Okay, integers, doubles, arrays, as I said before, is just to collect the data and also strings. Okay, so in the end, we have also some global variables that are probably used, for instance, the iteration number, okay, or how the data has been distributed or the process, if it is a native process originally created or a new one, that is the spam processes. Number of nodes, and in the end, what we have is the code that we show, for example, at the beginning, that is this one. As a summary, we need some instrumentation, and so we need to put some programming effort that probably requires of knowledge from the application developer. But according to our experience, that we are now implementing different applications, use cases, we think that this can be done, okay? And of course, once you integrate one application, it can just use all the functionalities and can be run with malleable capabilities that we think that is a good improvement, okay? So I think that this is the end of my talk, and now my colleague is going to introduce a more practical use case. I think maybe the questions can be at the end, okay? Because maybe Javi also answer the questions. Okay, thank you.
Okay, so basically, right now I'm going to show you how this framework works and give you some example of execution. For that, I have several demos that we can follow. For example, in this, I don't know if more or less, example C. In this case, we are using a Docker cluster with only 3 nodes, running with Slam, everything. And in this other case, we have a dual cluster, which is in Torino, with a remote connection and everything as well. And for the demo, we have several examples. But the ones that I'm going to show, take this out now, is we are going to use basically a very simple hello world example both in C and in Fortran. And also probably support of actual application, in this case, Wacom++, which is one of the use cases of the project. So first things first, let me show you the code of the Hello World example. It's basically what just David told us. Here we have the main code. For example, here you have the header that we have included. We have here the variables for the iteration and the iteration maximum number of iterations. This is basically the same idea for any API application, MPI init and ranks and size, but in this case, instead of using MPI Word or MPI Conword, we're using the ADM Conword. And then we have as well, well, here basically are getting the processor name, because we are going to print all the processor names, all the process involved, so we can see really how it's evolving the malleability, and they are all gathered iteratively. And here is the other part that is important on the code that is also interesting to check out. First, we get the attribute, which is the process type, and we get there if it's a native or it's a spawn process, meaning if it's one of the original created at the beginning, or it is one that has been spawned during the execution of the task. Depending on which case you can do whatever you need to do. Here we are updating locally the state of the iteration, both maximum number of iterations and the actual iteration number were really done, which is important for the spawn processes, because whenever you spawn, you don't know where is the application currently running, or you need to know in which iteration you should start. In this case, we are starting the monitoring service at the beginning, so we cover the whole loop. You can cover whatever you like, but in this case, it's covering the whole loop, so it's always monitoring. And then we have the loop here from the iteration, which iteration. And in this case, we are, and I don't know what here. We are using hints to the controller in order to say to it more or less what is the malleability we want. For the example we are going to do, we are not using any malleability manager or any malleability algorithm. So basically, the hints we are going to provide are the actual actions the intelligent controller is going to do. In other cases, this is just hints that the controller will consider or not, depending on whatever it's doing. But in this case, so we are going to follow the iterations, and whenever it is a certain number, we're going to increase the number of processing twice. In this case, once the first time it will increase in 2, and the next time in 2, and then later on it's going to reduce also in 2, and then also in 2. This is important. This is specifically designed for the Docker cluster we are going to use, because Docker cluster we are going to have 3 nodes of 2 cores each. So every time we include 2 more processes, we are including a new node. So we are going to increase 1 new node every time, and we are going to decrease 1 new node every time. And these values are hinted to the IC controller by updating the global keys, admin global hint number process, and hint exclusive. Exclusive process is another hint that is quite interesting to see, because if you want, you can say that every process will be executed on 1 single node. So depending on if your application is using MPI with OpenMP or something that is going to create many threads, if you want only 1 process per node, you can do that as well. But well, basically later we have just all gathered to get all the names, and here we get the malleability region starting. In this case, we're not doing any computation. We just going to simulate it by a sleep of 1 second, and then we are going to update the global iteration number. This has to be done before ending the malleability region. Okay, so it can be replicated to all new spawn processes. Lastly, we end the malleability region, getting the status, and depending on the status, we continue depending on if it's active. We just update the ranks and the size for whatever you are going to use them, and if it's not active, stop or whatever, you just break the loop and finalize the process. In this case, because we are monitoring the full loop, we have to stop also the monitoring service and then finalize as any other MPI application. So this is the code we're going to execute in C. So let's try it. In this case, we have here the 3 nodes. First node, well, you can see the name of the nodes. The first one is node. I think this is the first node, the second node, and on the top of the screen we have the third node. These are top applications. We are currently prepared to detect only the application we are going to use. And at the end, here we have running, well, let me close it so you can see it clearly, the IC server. So here it's going to detect all the calls to the IC server to shrink or expand the application. So let's execute that application. For that, we are going to use this one. We are going to run the application, and we are going to put also on the screen to see the results on the number of jobs. And if we run this, you can see first start on the first node. It's running. You can see here the SQ of the Slurm and jobs and the steps. There's only one job right now because it's only running on the first node. The moment it transfers to the next node, the idea is that the SQL server creates a new job on the Slurm and just execute the new processes on this new job by using SSH. It just applies MPH to use that. In this case, here is also created a new job. So now we have 3 nodes. Basically, you have several jobs, as many as branches as you are doing. Now it's shrinking, so it has to shrink one, the first node. Then it's shrinking the other one. Now it's only on the first node, and it's gonna end. Basically, that's the idea. In a few seconds, I think. Yeah, now it's ending, and that's basically the full execution. In this case, we can see that this is a very, it's not very difficult to modify an application that is actually in this kind of format with an initialization part and the loop to modify it to run in this way. We can try as well to execute this application on an actual cluster. Let's execute it on the Torino cluster. In this case, in the Torino cluster, we have to run first the Redis database. This is the server you're looking at the up screen in the left part of the screen. Down there is also the IC server, and now let's run the same application. Oh, I don't know if it's connected or not. Let me try because the thing is disconnected. I'm gonna connect it later, and let me execute for now. Yeah, let me execute another example here, and then we go back to the Torino cluster. When this connect. No, okay, yeah, that is working. Okay, so let me do this. Let's see if it works. Also nice, this one. Okay, let me see if everything is correct because. Okay, everything is working, so let's execute it. Well, let me, here it is. Extrude is 1 second. All right. So, Victoria, ATM. Okay, now it's supposed to run. Also, I forget to do something else. Okay, now it's in the middle of the execution, but I'm gonna start later again. So basically now it's running on 2 nodes, I think, and now it's running on the third node. We're going to expand the messaging. Yeah, now it's messaging all the nodes. In this case, because we have 36 cores per node, it's executing really, I think, the first execution only executes 2 processes, but for each new node, it's executing new 36 processes. So it's running 64 processes, I think. So every time we include a new node, we include a new number of 36 processes, and that's what you see in the screen. Now it's ended the third, is ended the last slum node. So now we only running nodes. Now we only have 38, I think. It's a little more because it's a little slower in this case. Now it's ending, yeah, now it's ending the second node, and now it's only running on one node, with only two processes. So it's the same as we did on the Docker cluster, but in this case, on an actual cluster, and now it's ending. Okay, also, just to check out, you can see how it's done this for Fortran. Fortran is here, showing the code. In Fortran code, it's basically the same idea, but just in Fortran. For example, we have to use the useAdmire wrapper as the header here. Then the only difference is that instead of MPI init, we have to use a different call, which is fMPI init, because everything else is the same. Of course, instead of MPI conword, we have to use ADM conword, and anytime we want to update it, we have to use an getCom call to get updated. But everything else is the same. Here we have also the processor name. We are gathering the names. And we are getting here the attribute of ADM global process type. And if it's native or spawn, we do whatever. We update here the iteration number and also the global maximum iteration number. We are starting the monitoring service outside of the loop. Then we start the loop here. And depending on the iteration number, we include two new processes. Well, in the case it will be 36. It's two processes because it's for the Docker cluster. Or if it's another iteration, we remove two processes. And later on, we just gather all the names, so you can see on the screen. We start the malleability region, just exactly the same code, but in Fortran. Then we sleep 1 second. We update the global iteration number. And then we stop the malleability region here. And as before, if the process is active, meaning it's continuing on the execution, we just update the ADM conword, and then we get the new rank and the new size. If it's not, we exit the loop, and then we finalize. We also have to use a new special function, which is fMPI finalize. But it's basically the same idea, just in Fortran. Let's execute it in Fortran to see how it works. So in this case, we just do the same, but for Fortran, which I have here. And basically, I mean, the printing is a little different, but it's the same program. It starts with the first node. It's running on the first node. Now it's running on the second node. In this case, you have just the printing of all the processes that are running right now. The third node, now it's running on all the 3 nodes, and we have all the printings. You can see also here in the messaging of the IC server, every time there is a string or a expanding, you have a message including what is happening. Well, basically we are reducing now a new node, sorry. Now it's reducing just to 1 node, and a few seconds is going to end, I think. Well, I mean, in a few seconds. Okay, now it's ending. And finally, to finalize the demo, let me show you one actual application, which is the Wacom application, which is actually running with this malleability. In this case, it's just an actual application with actual computing, but the same things apply. We have the same MPI init, and instead we are using the ADM conword instead of MPI. We get in the process type, native or spawn. We get in the iteration and the maximum number of iterations. We are starting the monitoring. You have here the loop. In this case, remember, we are using hints. We get the hints to apply, to expand or to reduce. We stop the malleability region, and here we have the code. The only difference with the code, which is the actual code of the application, is that you have to substitute every MPI conword with ADM conword, but everything else on the code is the same. You have here the full code of the application, up until the end, where you just update the iteration and finalize the malleability region. And then you do the active, get the actor. If it's active, update rank and the site. If it's not, it's ending, and that's it. So basically, you just add around the application, but you don't really touch the application that much. And if we execute that, let me put this so you can see what is happening. Okay, and now if I execute the application, now this is an application of a typical particle application, a typical application of particles, and basically every iteration is computing a number of particles, which is distributed across the process that are in the communicator. So every time you add more applications, more processes, the number of particles per process are reduced, so the application goes faster. That's why when you have 3 nodes, it takes a shorter time to get to the point. And when you have less nodes, it's really getting slower. That is the idea. So you can see that it's expanding and increasing as before. It's exactly the same idea, but now it's an actual application. And finally, in a few seconds, I think it's going to end with the final execution. Yeah. And that's basically the conclusion of the demo. Well, basically, I think I have shown you what we have up to now. And if you have any other question.
Okay. Questions? If you have question online, remember to raise your hand here virtually, I mean. And someone in the room?
I have one, but maybe because I didn't get the point. How data is, I understand that data is transparently redistributed. Once you add
You mean the keys, the values we are going to for the keys, for the registering keys, no?
I mean the data where the application is working, because even so, I suppose you have a big matrices that you cut in some way with a number of processes. Then when you add another process, that data is
Data redistribution, basically.
how data is redistributed.
I know what you mean. I mean, that first of all, this is an old feature of FlexMPI. But the point is, now we are adapting it to the actual version. So right now, in this version, is a work in progress, as David said. But the idea is, well, David really knows about much more than I do because it's his own work.
It's a question for both.
Yeah.
Yeah, but if you want to answer it, maybe.
Yes, basically, is we have 2 implementation, FlexMPI, the original one, and Admire one.
Yeah.
So Admire includes new features, and porting the data redistribution is a pending thing from FlexMPI to Admire.
Okay.
But this can be done because it's already done. It's quite straightforward. And what we do in FlexMPI is basically we consider dense and sparse data structures. So basically, the user register the structures following the same philosophy as we explained today, and specifies how the data is distributed. Basically, replication or distribution, blocks or cycling, general hints. And then the system, I mean, FlexMPI library, transparently distributes the data. So for dense matrices, it's quite simple because it's just, but for sparse, it's a bit more difficult because we take into account the number of non-zero elements. So it's not distributed by rows or columns, but by elements in order to keep the dual balance. Okay. Yes, but nice thing is that it's done transparently, so you don't need to do anything. Yeah.
Yeah, good. Thank you.
Any other question?
Okay. Thank you.
Thank you.